Hello everybody, here is your promised review for the test review. We'll be looking at the trickiest questions, starting with number 2. On this question you're asked which quantities are the same going up as they are going down, so let's look at two spots. This spot on the going up side, this spot on the going down side, and let's begin with each quantity. First of all, recognize that there is a difference between speed and velocity. Speed is just how fast you're going, but velocity also includes direction. So velocity is a vector, but speed is just a number. So at this spot right here, maybe you're going up at 3 meters per second, but you're also traveling at 3 meters per second here as well. So the speed is the same going up and down, but the velocity is not, because here we see a positive velocity. Actually, if we looked at the full velocity here, because there is some x and some y velocity, we have a velocity that looks something like that. And here we have a velocity that looks something like that. And those two velocities clearly are not equal. So those are not the same going up and down. How about the acceleration? Well, the acceleration is just the acceleration due to gravity, and of course that stays a nice steady negative 9.8 the whole way through at all points. So the acceleration is the same in both going up and going down. The x velocity, you can see, doesn't change. It stays the same throughout the whole flight. There's no accelerating agent that pushes you faster in the x direction. But the y velocity, as you can see, does change. It's positive here, negative there. So that's a changer. And the gravity force, like the acceleration, stays steady. Remember, you can always calculate gravity as mass times 9.8. It's always directed downward. So that's the same before and after. Let's go on to our next selected question. A little reminder on how to add vectors. Remember that when you do add vectors, you want to assemble them tip to tail. If it's not a right triangle, you can't use sines or cosines or tangents or Pythagoras. You have to either draw it out or use some other sophisticated thing like law of sines or law of cosines. We'll just draw it out here. The two vectors are assembled together as an added situation. And now we can draw the resultant vector. That's from the beginning of the first to the end of the last. That's the vector we're interested in. You can see it's a fourth quadrant vector pointing in this direction. And if you measure the angle with a protractor, you'll see it's about 18 or 20 degrees down from the x-axis. Let's say 20 degrees is what you measured, let's just say. And so that would make it a 340 degree approximately angle. That's the direction. How long is it? Well, it's longer than 4. But not quite 6 long. If you measure this to scale, you can determine how long each unit is, break that up into 4 pieces, scale it out along this line, and you'll see that it's approximately 5.5 meters long, thereabouts. Maybe a little bit less, maybe a little bit more. So approximately our resultant vector is 5.5 meters long at 340 degrees. Next question. This is number 8. So on the whole trip is a 6.8 second trip. But if you look at the whole trip, you'd have this as your starting point and this is your ending point. And that wouldn't tell you anything about how high up you got. So you have to break the problem in half. Instead of looking at the full 6.8, chop it up in half. 3.4 seconds going up, 3.4 seconds going down. and we can look at just the second half of the trip. It's helpful to look at the second half because if you do, the beginning velocity at the top would be 0, which is great because in the equation d equals 1/2 at squared plus v initial t, the initial velocity being 0 gets canceled out. That term goes to 0. And so you're left with a falling problem. The distance is what you want. The acceleration presumably is the acceleration of gravity on Earth, negative 9.8. Check, you know it. 3.4 seconds for this event. Check, you know it. And you can easily figure out the distance. It should come out as a negative value if you choose that as your origin. That's fine. We're just looking for the magnitude of that height, just how tall it is. So you can disregard the minus sign. Okay, next question looks like number 12. On that one, you're told that a net force of 5 newtons accelerates some unknown mass with an acceleration of 4 meters per second. It's easy business to figure out the mass in that equation. It should come out to 1.25 kilograms. And now the question is, what happens if instead of a 5 Newton force, what if we have now a 10 Newton force on the very same mass, 1.25, and you can see that calculating the acceleration is a straightforward business. Let's see, next question. Okay, this one's kind of complex. You probably have an intuition if you're just looking at this that this tension force, which is called T2, just intuitively, gut feeling, has to be a tighter string than this one, T1. But that doesn't solve our problem completely because we have to think, for this problem, we have to think about the x and y components of both of those tension forces. So it's helpful to begin by thinking about the x components of each tension force, because it makes sense that the x component of T1, whatever it is, has to be absolutely equivalent to the x component of T2. If those two x components were different, the ball would start accelerating to the left or to the right, and you can see just by inspection that's not happening. So you can see that T1x and T2x simply must be equal. And that's the beginning insight into the problem. T1x, T2x. Because this helps us now think about the tensions in the y direction. Let's draw those in. If this is T1x here, T1y must go upward. This string definitely pulls upward, and we must stop right there so that when we add the x and y component, we end up with something that lines up in total. The total tension has to line up along that string. So here we have Tx1 drawn. Let's label, let's go to blue. Let's call this guy T1y. T1y. And similarly, we have to do the same thing with the tension on the other side. Hopefully it makes sense to you that this tension force must continue upward until it's in alignment with the total tension, so that the x and the y line up to give us our total tension, T2. Remember, the key to the problem is recognizing that the two x tensions must be the same. So this is T2y here. And now the rest of the problem is pretty much solved for you here. You can see the sizes of T1 versus T2y. And you can also see the sizes of T1 versus T2. Just to finish the problem off, the gravity force on the ball, of course, will run down. How big will it be? It'll be as big as T1y plus T2y, so that there's no net force in the y direction either. So that's the gravity force. And there's a complete force diagram. Okay, let's see. I think there's one more to briefly discuss, and this is number 17, the one with the penny on the record player. Of course, there must be some sort of force guiding it in its circular path. That force would be a friction force. It's the only possibility. It must point to the center. Since it's going in a circle, there must be a centripetal force. That force you could call the frictional force on the penny from the record, and we'll just agree to call that FPR, frictional force from the penny. Sorry. On the penny from the record. But according to Newton's third law, there's got to be one that's exactly equal and exactly opposite. It's also going to be a friction force, and it's also, and it must be on a different object. This will be the frictional force from the penny on the record. We should call that something like FRP. And according to Newton's third law, those guys must be exactly the same size, but in opposite directions. So this tugs on the record outward. Of course, there's other molecular forces on the record tugging it inward that are even stronger, but there's at least something pushing it outward. Okay, next question. On question 18, the only thing I wanted to discuss was the second part. Was this a constant velocity vector? Well, the magnitude is constant. It's always going the same speed, but notice that the vector is definitely changing. Not its length, but its direction. And that counts as a change for a vector. So it's not a constant velocity vector. Thus, we have acceleration. Next question. So when we speak of a position time graph, we're talking about a distance time graph. And you might remember from earlier in the year that the key thing to remember about a distance time graph is that it shows the velocity of the object. But it shows it by the slope of the line. So, for example, if we have a positive slope, that means we have a positive velocity. If we have a zero slope, that means we have a zero velocity. And if we have a negative slope, that means we have a negative velocity. If we're trying to show acceleration, remember that acceleration is a measure of how the velocity is changing. If the velocity is on the increase, meaning that the slope is on the increase, that means we're accelerating. So does this show our velocity increasing? Yes, because it shows our slope increasing. So this, or more correctly drawn as a smooth curve, this would show acceleration, and you can use your imagination to show what deceleration would look like, and then constant velocity, in other words, constant slope, might look like. There are a number of possible correct answers, but they will all show the slope behaving exactly as you want the velocity to behave. Next question. On this one, you're asked to find the tension force between the two blocks. The hint I'll give you on this one is you want to first choose as your system both blocks together. And if you choose that as your system, this force, which is 12 newtons pulling us to the right, would become the net force. And these two tension forces for our system are internal and therefore canceling. They are Newton's third law forces. So this 12 Newton force drives the whole system. From that you can figure out the acceleration. That's an intermediate step. And then once you know the acceleration, you can choose either the 1 kilogram block or the 2 kilogram block as a smaller system. Use this same acceleration and figure out the tension force there. And next question. This one is kind of a tough one. We've got a force at an angle, and we're trying to figure out ultimately the normal force. So let's begin by drawing and identifying the forces that are acting on this block. So there's this force W going straight down. They call it W. Remember that W is one of our options for labeling the gravity force. We could call it W, which stands for weight. We could also call it mg. Same animal. What other forces do we have here? Well, we're interested ultimately in the normal force, so let's draw it. The normal force would go up and toward the object, away from the surface causing it. Let's label that as a normal force, since that's what it is. And it might be tempting to just say, oh, the normal force is equal to the gravity force. But wait, there's another force over here, this tension force pulling off at an angle, which pulls somewhat to the right, but importantly, somewhat upward. And this force right here is going to be related to the geometry of the triangle. If this angle is theta, and we can say theta is 30, I suppose, because that's what it is, then this force right here going upward would be F sine theta. And if we look at the y direction, we can see three forces at play. Two positive forces and one negative force. So in the y direction, we can say F net equals ma, but ma will equal 0 since there is no acceleration in the y direction. So I would expect to see three forces here, a positive normal, a positive F sine theta, and a negative mg. And those three forces together should add up to a grand total of 0, and then your job is to solve for the normal force. Next question. Okay, on this one, number 23, we've got a diver running off a platform horizontally, which means that the initial velocity is purely in the x direction, no y velocity to begin with at all. So in our y equation of motion, this term right here, the middle term, will go away. There is no starting y velocity. It's purely x. And we're attempting to figure out how much time it takes, t, to get to the ground. And you can see we know we have to choose a coordinate system, right? So let's go ahead and do that. Coordinate system doesn't matter where, but we could do it here, I suppose. That makes our initial distance 0. And our final distance would be -5 because it's below the origin by 5 meters. And we can solve for t. Of course, A on Earth, -9.8. Next question. 24. We have a diver moving initially with 3 meters per second, horizontally again, and he lands in the water 4 meters away from the base of the cliff. So we know a lot about the x world. We know the starting speed and presumably the continuous speed in the x direction. Remember that the x velocity never changes. 3, that's probably a bit too fat. Let's try that again. How about this? 3, 3, 3. So there's no real concept of an initial velocity in the x direction because it never changes. It's the initial, it's the middle, and it's the final. We know Vx to be 3. I actually have written this equation incorrectly. Let me fix it up right here. This is the initial distance. Whoops. Well, give me 1 second. Let's make that in black. Initial distance. There we go. Much better. So we know the velocity is positive 3. We know we can figure out the time in the air because we know the final distance is 4. So we can figure out the time in the air. Once we know the time in the air, we can make a new problem where our starting velocity is not 3 meters per second, but is 9 meters per second. Does that affect the time in the air at all? Nope. The time in the air is completely controlled by gravity and how far you're falling. Sideways motion does not affect the rate that you fall. So it'll be the same time in the air, whatever value you have here is still good in our second problem. Same equation, same time in the air, new velocity, and therefore new final distance in the x direction. Next problem. Number 25. This is a good one. A pendulum, when it swings, traces out a path that is partially circular, at least at the bottom here. And we know how to handle anything that moves in a circular path, even if it's just for a while. We know that we can describe the acceleration as v squared over r. And if we examine what's happening force-wise at the bottom of the arc, there are but 2 forces. There's a tension force going up. Actually, let's make that a little fatter. There's tension force going up, and there's a gravity force going down. Those are the only 2. You should know that the gravity force must be smaller than the tension force because the net force has to be toward the center. Remember, anytime it goes in a circular path, the positive direction is up, and the forces must balance out so that the net force points toward the center. So when we describe the net force, we include both of our forces, T positive, mg negative, and together they must equal ma, but our a gets replaced with, of course, v squared over r. And in the problem they give you v, they give you r, so you know a completely, they give you m, so you know m completely, you know mg, and your job is just to determine the tension force. Next problem. For this one, you're asked to draw acceleration, velocity, and force vectors at the 3 points on the arc down below, and you should probably take a look at the earlier discussion of problem 2 where we sketched out those vectors briefly on a different arc, a little bit skinnier arc but still an arc, and the thought process is the same for both. Let's take a look at the last problem on this page. Okay, this one goes back to vector days. We've got a truck traveling at 50 meters north for 10 seconds. Then he takes a sharp turn and travels 120 meters to the east for 55 seconds. And we're asked to figure out the magnitude of the average velocity. So we're not concerned with the direction, even though we do know it's going to be, let's actually draw out that vector. We do know it's going to start here and end here, so that would be the direction of the velocity. But we just want to know how big that is. We have to be careful because We're not Pythagorasing the distances, not 50 and 120. Well, maybe we can actually. Since the velocity is the distance divided by the time, we can actually figure out what distance we're covering here. We start at this moment, this location, this moment, and at this location, that moment. How far have we traveled in total? 50 that way, 120 this way, but in vector language all we care about is the starting and ending position. So to figure out that total distance, let's just call that, let's see, I guess in the normal style, we can just call it our total distance d, from one end of the arrow to the other. And if we Pythagoras those, it should be the square root of 50 squared plus 120 squared. And I think you'll find out that the calculator tells you that that comes out to 130 meters. So we have traveled a grand total of 130 meters. Actually, our displacement is 130 meters. We've traveled further. We went this way than that way. But all we care about is our displacement. How much time did it take? 10, 55, 65 seconds in total. So our time is 65 seconds. Our displacement is 130 meters. Therefore, our average velocity will be this number, whatever that works out to be. It looks like it's exactly 2 meters per second. And that's the magnitude of our velocity. The direction is a first quadrant angle along that path. But that's not asked for. Number 28. As soon as you see a pulley, you should instantly recognize that you need to straighten out that system so you can see how the forces interplay with each other, how they align. You have 3 forces in the direction of the acceleration, 2 tension forces which will self-cancel if you choose the whole thing as your system, and then 1 force, the gravity force on this little mass, whose mass is unknown. It's just called m, so that makes the gravity force mg. So let's choose the whole system. Since it doesn't really matter what part of the system we choose, everything's going to accelerate together. And if we're clever and choose the whole system, we can ignore these 2 internal tension forces. We can ignore the 2 up-down forces that never rotated as we swung the mass out. And so the only force that comprises the net force would be mg. mg is our net force. There's nothing else. Now, what do we use for the m of our system? Well, we've got 2 pieces, so I've got an m, I've got 3 more m's, so in total 4m should be my mass. And then from there, solve for the acceleration. You'll notice that the m's nicely cancel away. Next problem. On this one, we're tracking the Vy, Vx, and acceleration as an object goes in projectile motion. Recall that the acceleration doesn't change too terribly much. In fact, it stays at a nice steady negative 9.8 at every location. Never changes. Negative at every location. So I would expect that when you were plotting the acceleration at every particular moment in time, that you had a nice steady negative value. Negative 9.8, negative 9.8, negative 9.8, negative 9.8 throughout. How about Vx? Well, Vx, once it's launched, should not change. There's no accelerating agent in the x direction. If we know the Vx here, it'll be the same as the Vx here, it'll be the same as the Vx here, always positive. nice and steady. So in the Vx, we should just get one steady positive value. How about in the y direction? Well, that one's a little different. For the y direction is ever changing. At first we start with quite a bit of y velocity, then less still. At the top, 0 y velocity, 0 y velocity at the top, 0. And then as time goes by, we start to observe some negative y velocity, first a little bit, then a little bit more, then a lot. And so the y velocities are changing from positive values to begin with to negative values to end with in a nice steady fashion. Next question. Just wanted to remind you, gravity force can be expressed as F sub g, can be expressed as W, which stands for the weight, or it can be expressed as mg. All three of those things are equivalent. Next question. On 33, we've got an object that's released on some new planet, so you can't use 9.8 for the acceleration. That's what we're trying to figure out. What is that acceleration? We don't know, but we want to know. If it's released from rest, you can say the initial velocity is 0. The time is given to you, and so therefore you should be able to solve for the acceleration. Remember, you get to choose your coordinate system. You can set your initial distance to be 0 if you so desire. That'll make your final distance in the negative territory. Next question. Number 34, just a hint. The velocity vector and the acceleration vector should be perpendicular to each other at right angles. Make sure you get that right. Okay, we are ready to look at the last page now. On problem 39, you're asked to identify the forces on an Eskimo child who's on a sled on a frozen lake, and he's being pulled to the east that-a-way, but key fact, he's being pulled at a constant speed. So that means there can be no acceleration and therefore no net force on the child. So let's take a look at the forces that must be present. We can be sure right off the bat that there's a gravity force. May as well draw that. That's never going to disappear. And there must be an upward force to balance that. That would be the normal force. So let's now examine the sideways forces acting on him. You might suspect that there's some kind of a friction force on him, maybe pulling him forward, but you'd be wrong, because if that was the situation, these two forces, the red ones, would cancel. The blue one would produce a net force and therefore an acceleration on the boy. And you'd have to find some other backward force to balance out that one so that there was no net force. So there can be no net horizontal force. If the mom suddenly starts pulling faster, indeed there would be a friction force pulling him forward, or if they hit a rough spot of ice and the sled slowed down, he would continue moving forward, and then he would feel some friction slowing him down from moving forward on the sled. But at a constant speed, there are no horizontal net forces on him. By the way, if you'd like to get a little extra bonus, extra credit for the review, on your diagram of the Eskimo on the sled, if you take time to draw a little Santa Claus hat on the Eskimo, I will know that you have listened to this review, and I'll give you a little extra bonus for your studious ways. Next question. Let's take a look at this block. He's being pulled by, it's a block of cheese, I believe. Yes. and it's a 10 kilogram block of cheese. That will become important later on. And we're trying to determine the coefficient of static friction. We're told that 60 newtons is just enough to get us to slip. So that we're on the verge of slipping. We're just about to move, but we haven't moved yet. So like always, that means the acceleration is 0 to begin with. So let's examine our horizontal forces. We've got this 60 Newton applied force. Maybe it's a tension force. And there must be some friction force going the other way. And right now, this 60 Newton force is a positive force, pulling us forward. The friction force is a negative force, slowing us down. We still are trying to get mu static. But remember, we can replace the friction force when we're on the verge of slipping as mu static times the normal force. So all we need to do is determine the value of the normal force here, and we're home free. And that should be an easy matter at this point because you've got a gravity down, mg, you've got a normal up. Those must be equal. So that normal force must exactly equal that gravity force. So the normal force is known, check, and you can solve for the static coefficient of friction. Last problem, 43. Here we're adding two vectors, vector A, vector B, and we need to add them precisely in this problem. I mean, you could get a rough idea by doing the old connect the tip to tail, then draw a vector, which is the shortcut from the beginning of the first vector to the end of the last. You could even estimate it. You could estimate the angle, you could estimate the size. But here we're looking for precision. So we want to be precise by breaking each vector into its component. So here's vector A. A in the x direction is 20 cos 40. A in the y direction is 20 sine 40. Notice both of those are positive, positive x, positive y. If we take here a look at vector B, we can say bx is, whoa, we got a little problem here. I need to do a little editing. Stand by for a second. Stand by for a second. Bx, by, bx, by. No, actually that's right. I don't know what I'm worried about. B in the x direction is, oh, I see what I'm worried about. I got my sines and cosines mixed up. Let's see, so this should be cos for the x direction, and it should be sine for the y direction. Okay, there, we're good to go. So in the x direction, we got 30 cos 150. Notice that points in a negative direction. That says our x component is negative, which makes sense looking at it. But our y component is positive, 30 sine 150. That's 15. So we're going to now add these two guys up, and so to be precise, we can say that vector C, that's what we can call this blue guy, vector C equals vector A plus vector B. So we add the components individually, AX plus BX, AX plus BX. Similarly, AY plus BY, that'll give us C in the Y direction. And then once we've got a good description of the X and Y components of vector C, we can figure out the magnitude by Pythagorasing them, and we can figure out the direction by inverse tangenting the Y and X components. Remember, when you inverse tangent, you always need to think about it, because the thing that you have figured out had better be, in this case, a quadrant 2. a quadrant 2 vector. There's always a chance because there are two inverse tangents that satisfy this equation, one in the second and then one 180 degrees away in the fourth, so make sure that your angle comes out as a second quadrant angle. That concludes the review, at least all the ones that we're discussing here. You should do well on the final if you've understood all of these. Good luck to you, and I will see you at our next instructional video.